Ooh, good morning. Tweet that we're starting. Sounds good on the monitor. Waiting for Kaggle. All right. Still waiting for YouTube to start. And YouTube is live. Hello. Good morning, everybody. Let me pause and turn off the sound so I'm not listening to myself in a echoing acoustic hellscape. Today we are starting a new paper, and it is Dissecting Contextual Word Embeddings, Architecture and Representation, and it was suggested by Leonardo Apollonio, or Leo Apollonio on Twitter. So thank you for the suggestion. I think we'd, one sec, sorry, let me move the mic to the place where the mic sounds good as opposed to the place where the mic sounds awful and echoey and distant. So thank you, Leo or Leonardo, for suggesting the paper. We'd talked about contextual word embeddings a couple of times when they came up with other papers. And I think it looks like a really interesting paper, talking about the sort of where we're at right now with them and how different architectures affect the type of contextual embeddings that you get out. And I just realized I cannot see the YouTube chat. Vahid says, hi from Tehran. Hi. And Cool Locust says, hi Rachel, how are you? I'm good. I'm grumpy on account of daylight savings time, which, fun fact, the Washington State Legislature, both the House and the Senate, have voted to do away with the time change and always just be in daylight savings time. It still has to go to the governor, and then it would need to be approved by U.S. Congress, but hope is nigh. And I would be delighted because every year it's worse and worse and worse, and it just feels worse in the body, and I'm not into it. Anyway, so we're going to be talking about contextual word embeddings. So this paper was from EMNLP last year, so Empirical Methods in Natural Language Processing, which is one of the big ACL, Association of Computational Linguistics conferences. So unlike the last couple of papers we've read, this one has gone through peer review, which is kind of nice because I feel a little bit less responsibility to be like, you know, really, really on it 24/7 and just like, oh, are you sure about that? Is that true? So that'll be nice for me. Vamshi from India, hello. And Vahid said, it's nice to see you. Oh, thank you. My computer can now handle video and also streaming right now, so it's a nice improvement for me. And Lakia says, Kaggle's the best thing in the world. Oh, I like Kaggle too. So let's jump in. Oh, and some background. So the Allen Institute here in Seattle, we keep reading papers by researchers in Seattle. That's not like intentional. It just worked out that way. Was funded by Paul Allen of Microsoft fame, and is just a big research institute. And I think they're going through a pretty big sort of like internal, like, what's our point now? What are we focusing on right now sort of moment. So I don't know if this is going to continue to be something that their research teams are focusing on. I'm not that like tuned into their whole thing. And then Luke is from University of Washington, which is where I got my degree. And we've chatted a couple of times. I don't know if he would remember me, but maybe he'd recognize me if he saw me again. And of course, the Allen Institute and the Allen, as in the Paul G. Allen Computer Science School at UW, are the same Allen. He's given a lot of money to computer science education, or gave, I suppose. He passed in Seattle. Coffee. Wait for my glasses to unfog. Aravind and Sumit say hello. Hello. All right. Contextual word representations derived from pre-trained bidirectional language models, BILMs, have recently been shown to provide significant improvements to the state-of-the-art for a wide range of NLP tasks. Oh, and someone asked last time what state-of-the-art means. So sort of like accuracy on a task is a high watermark. And if your model currently has the highest reported accuracy on a given task with a given like set of parameters, then you have state of the art is sort of the idea. It's like being top of the leaderboard at Kaggle. Very similar. Blah, blah, blah. However, many questions remain as to how and why these models are so effective. In this paper, we present a detailed empirical study of how the choice of neural architecture, e.g. LSTM, long short-term memory, which is a type of recurrent neural network, CNN, convolutional neural network, more commonly used in image processing, but people do use them in NLP, or self-attention, which I believe is what the sort of literature is coming towards calling transformers, Attention is All You Need is sort of the paper that lays out that architecture, and we read that a couple papers ago, so you can go and check those videos out if you're curious. Influences both end task accuracy and qualitative properties of the representations that are learned. We showed that there is a trade-off between speed and accuracy, but all architectures learn high-quality contextual representations that outperform word embeddings for 4 challenging NLP tasks. Additionally, all architectures learn representations that vary with network depth, from exclusively morphological-based at the word embedding layer through local syntax-based in the lower contextual layers, to longer-range semantics such as co-reference at the upper layers. Together, these results suggest that unsupervised BLMs, independent of architecture, are learning much more about the structure of language than previously appreciated. Okay, interesting. So they're saying a couple of things here. So one is that different architectures are learning different things, and that you can either have, and you're going to have to choose whether you want something that's fast. I'm assuming fast to train, and that this is speed at training time and not speed at inference time, but we'll get into that. Or it's going to be really accurate. That contextual representations outperform embeddings, word embeddings. So word embeddings are usually done at sort of a bag of words type of model, so that you'll say that these words occurred together in a sentence, but we don't know their how close they were to each other, their position relative to each other, and that including positional information gets you more learned structure, I think is what they're getting at here. And then as you go from the word embeddings up, you begin to get sort of like higher and higher levels of linguistic structure. So you start out with morphology. So morphology are things like the S in cats, that means that it's plural, those smallest units of linguistic meaning. And then things like local dependencies. So I ate a red apple, the fact that red describes apple, and that's the direction of the relationship. And then things like co-reference, so that if you're looking at a paragraph and someone is referred to by name in the first sentence and pronoun in the third sentence, you can figure out that those are the same person. So that's what I'm getting from this so far. Fingerdraw says, is there a way to train these models and Kaggle and download the model file or save it to Google Drive? Yeah, so if you write your file, your model, and usually people do HDF5, I think. It's the type of file structure that just like is soup to me and my dyslexia. So a hierarchical file, you can save that to your output, and then when you commit your kernel, it will show up in the output files section of your kernel, and you can actually create a new kernel on that if you like. Nick Chuba says, it's great to see you again. Oh, thank you. And then on Twitch, RolandU32 says, good morning. Glad to see video stream issues appear solved. They are. The solution was that I got a new computer with a graphics card that wasn't melted, and it was much better all around for me. And you guys. So this is really interesting. Yeah, let's get into it. So thank you, Leo, for suggesting this paper, because it's not something, like, I think I'd heard people talking about it a little bit, but it hadn't made a huge splash. It came out last year, and I think it's only been cited like 5 times. Actually, use my little Google Scholar plugin. Oh, okay. Used to be able to copy from PDFs. Or maybe I'm making that up. Yeah, so it's only been cited by 5 people. If we check out the Scholar profile. Oh, nope, it doesn't take me to the profile. It takes me to the archive version, and not the ACL anthology version, which is the one that we're looking at here, which is the post-publication version as opposed to the pre-publication version on archive. So if you're ever reading a paper that's available on our ACL anthology and archive, you should use the anthology. Nico says, I hope Kaggle will do reading streams more often. They're awesome. Oh, thank you. We'll see. I've got a really busy summer coming up. But I'll try to at least keep it to once a week. I don't know that I can commit to more than once a week right now. But I can ask around and see if anyone else would be willing to. Okay, contextualized word embeddings. So the original citation for this is Peters et al. 2018, and I'm not actually super familiar with this. So, yep, see, here's the archive version, and then there's the ACL anthology version. Which is not secure. Okay, I know they're in the middle of like porting it from a new version to an old version. So Ali says, despite me not understanding 65% of this, your enthusiasm keeps me engaged. Sorry if I got your name wrong. Oh, no worries. I don't even notice how people spell it. Like I mentioned, I'm dyslexic, so I'm just like, there's an R at the end, there's an L at the end. There's an R at the start, there's an L at the end. It's probably me. Okay, so this was, oh, I see. So it's the same Peters as the first author of this paper. So it looks like they're sort of expounding and building on their previous work. It looks like Mohit and Matt aren't on this paper. Okay, and then Luke was on the original paper as well. Oh, and Kenton. I know Kenton. Okay, so they're suggesting that you want to model more than just sort of what words occur together in some text. And you want to look at how the uses vary across linguistic context to model polysemy. So polysemy is where the same word can have multiple meanings. So the example everyone uses is like a bank can be the bank of a river, so like the dirt that comes down by the side of the river, or it can be like the building where you put your money. And being able to tell that those are different things is a hard task if you're using character level models and you don't consider the larger linguistic context. I mean, it's easy for humans, but it's hard for computers. Our word vectors are learned functions of the deep internal state of the internal states of a deep bidirectional language model, which is pre-trained on a large corpus. We show that these representations can be easily added to existing models and significantly improve the state of the art across 6 challenging NLP tasks. Blah blah blah. We present an analysis. Okay, so they're building on their earlier work, and hopefully they will talk about it in some depth. Derived from pre-trained bidirectional language models. So you train a language model and then you take the weights from that model and then use those as inputs is what I'm kind of getting here. And lots of tasks, including question answering, entailment, and sentiment classification. Entailment we've talked about a little bit in some other videos. So it's sort of a logical entailment. So if I say, like, I have 5 cookies, it's also true that I have 3 cookies, right? Having 5 things entails having 3 things logically. Logically in the sense of formal logic, which is not always the most human-friendly way of representing information. Sentiment classification, so how do people feel about things? Constituency parsing, so first you have to believe in constituency, which is a linguistic construct. So sort of showing that some chunks of words have a closer relationship to each other than other chunks of words. So like, I left the pizza on the table. On the table has a closer relationship to each other, those words together, than pizza on those 3 words have a less close relationship. So there's a constituency structure that you can use to capture that. Named entity recognition, so identifying parts of a text that refer to specific things like Disneyland or Tokyo, or I'm stuck in the Disney thing right now, Sleeping Beauty, so things that have names. And text classification, so just like classification but with a body of text. Despite large gains, typical relative error reductions range from 10 to 25%. Okay. We do not yet fully understand how or why these models work in practice. In this paper, we take a step towards such understanding by empirically studying how the choice of neural architecture, e.g. LSTM, CNN, or self-attention, influences both direct and task accuracies and the types of neural representations that are induced, e.g. how do they encode notions of syntax and semantics. Okay, so because these contextual representations are being extracted from a trained model, they're training models using several different approaches and then extracting equivalent, contextual embeddings from each of these, and then they're comparing those embeddings and also how well the model works on given task. Okay. Previous work on learning contextual representations has used LSTM-based BiLMs, but there is no prior reason to believe that this is the best possible architecture. It was certainly in 2016, 2018. In 2018, people were starting to get more into CNNs, and that's also the year the attention paper came out. No, that was 2017. So by that point, people were talking about transformers and fully attentive models or self-attention models. But bidirectional LSTM with attention still had and has state-of-the-art on many problems. So just sort of, if you were like, I want to pick a model architecture for an NLP problem, but I'm not telling you what the problem is ahead of time, I don't know why you do that. Probably many people, I think, would choose bidirectional LSTMs with attention. Mayar says, hola. Okay, so that was sort of like the trendy thing at the time, but they're saying that there's no reason to believe that that's the best thing. More computationally efficient networks have been introduced for sequence modeling, including gated CNNs for language modeling, Dauphin et al. 2017, and feed-forward self-attention-based approaches for machine translation, Transformer, Vaswani et al. 2017. That's the attention paper I mentioned earlier. I don't know what a gated CNN is. Let's look that up. I'm actually going to see if I can find like a... just want to see if I can find like a blog post instead of a paper, because I think that would be a little bit faster to read, a little bit faster to get into the eyeballs. I'll check out Towards Data Science. They have some good stuff. How to build them from scratch. Okay. No, I want to know about what they is. RNNs are inherently sequential. Yes. All the elements in a CNN are processed simultaneously, which can speed up processing immensely. Yep, this is a bottleneck that we've talked about before when we were talking about the attention paper. Blah, 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 Dauphin et al., that's the same citation they had. Produce results comparative with CNNs. CNNs can process information in parallel. Okay. I'm trying to figure out what the gating is. Blah, blah, blah. More talk about what RNNs are. Talking about what convolutions are. Normal convolution, causal convolution. The input is zero padded on the left with k minus 1 to 2 equals 2 elements. So this is sort of condensing up, and this is sort of condensing up but not looking at the future. Gated linear unit with residual skipped connection. A convolutional block with window k equals 3 produces two convolutional outputs, A and B. A is element-wise multiplied with sigmoid B, and the residual is added to the output. Image modified from this video. Oh, I feel like... Okay, so it looks like it's using the same thing as, and feel free to jump in with the comments if you're more familiar with this architecture. So it looks like more or less the same thing as a forget gate from LSTMs. That's one of the things that makes it LSTM, is that it has the ability to sort of forget things. So it looks to be pretty similar architecture-wise. Defining it's a mechanism called a gated linear unit, which involves element-wise. B contains the gates that control what information is passed up to the next layer in the hierarchy. Conceptually, the gating mechanism is important because it allows selection of words or features that are important for predicting the next word, and provides a mechanism to learn and pass along just the relevant information. So similar to attention. Similar to ReLU, the gating mechanism also provides the layer with nonlinear capabilities, while providing a linear path for the gradient during backpropagation, thereby diminishing the vanishing gradient problem. So it's the... I don't know what I was going to say there. Okay, I have like a very surface level understanding. I will keep reading about those in more depth if they seem to be super relevant to this paper. I'm much more familiar with RNNs than CNNs just because, again, my background's in NLP and, people are still using LSTMs in all sorts of places, and that's a flavor of RNN. The R meaning recurrent. Okay. As RNNs are forced to compress the entire history into a hidden state vector before making predictions, while CNNs with a large receptive field and the transformer may directly reference previous tokens, each architecture will represent information in a different manner. Okay, so they're saying that RNNs, you sort of have like one value or vector that you're looking at that's representing everything you've seen before, and that with CNNs and transformers, you can just look at the tokens that you've seen before that might be particularly relevant. So they're suggesting that this is going to be reflected in their sort of like general way of storing information, which I think makes sense. Given such differences, we study whether more efficient architectures can also be used to learn high-quality contextual vectors. Previously, they'd learned LSTMs. And efficiency here is in training time, because in RNNs, you have to sort of like step through sequentially, because that's the way the network architecture works. Whereas with CNNs and transformers, you can look at all tokens at the same time. So it's not necessarily faster to train, but you can parallelize it, which will then make it faster. So if you don't have access to any sort of GPU, which everyone does on Kaggle, then it's not necessarily the fact that a transformer will always be faster to learn, but with parallelization it can be faster, or CNNs. Blah blah blah. Where was I? Given such differences, more efficient, there we go. We show empirically that all three approaches provide large improvements over traditional word and vectors when used in state-of-the-art models across 4 benchmark NLP tasks. We do see the expected trade-off between speed and accuracy between LSTMs and the other alternatives, but the effect is relatively modest and all 3 networks work well in practice. Okay. Given this result, is it important to better understand what the different networks learn? Preach. In a detailed quantitative evaluation, we probe the learned representations and show that, in every case, they represent a rich hierarchy of contextual information throughout the layers of the network, in an analogous manner to how deep CNNs trained for image classification learn a hierarchy of image features. Ziegler and Fergus, 2014. I have no idea what a hierarchy of image features would look like, but I guess they learned that, huh? For example, we show that in contrast to traditional word vectors, which encode some semantic information, arguably, the word embedding layer of deep BLMs focuses exclusively on word morphology. Moving upward in the network, the lowest contextual layers of BLMs focus on local syntax, while the upper layers can be used to induce more semantic content, such as with in-sequence pronominal co-referent clusters. So I think that the pronominal co-reference clusters would be something like, Bill and Sally are coming for dinner, they don't like fish, and knowing that they refers to Bill and Sally. maybe. Ryan says, funny coincidence, in the GCNN paper at the end, they mention clipping gradients and norm and show it works really well. The system basically doesn't work without it. Oh, interesting. And I think that's a coincidence because there was a paper that came out recently that showed that batch normalization will always result in exploding gradients. And Ryan was mentioning on Twitter that he uses clipping and norm, I believe. I can go back and find the tweet. And that he has had good results with it. Yeah, I don't know. It's every so often, I feel like I've got a pretty okay handle on the NLP research, but the machine learning research is like, I don't know, it's like when we found out that dinosaurs were feathered, but like constantly some sort of like fundamental assumption that I had about machine learning and deep learning architectures based on like what I'd been told and what I'd learned previously is just like, actually, we found out that that is not the case, which is exciting and frustrating because you have to keep relearning stuff. That's good. Keeps you sharp. Okay, so basically, I think I've mentioned on the channel before, in linguistics we have this idea of sort of the hierarchy of language, where low-level things are things like speech sounds or the parameters of sign language, and then as you move up, the units become bigger, and we would say that's sort of like more high-level things, and the thing that they're proposing here is that the information that is learned at each level of this bidirectional language model is moving up that same linguistic hierarchy, more or less. So starting with morphology, moving on to syntax, and then things that I would call more like discourse level co-reference. So that's really interesting. Sagar says, hierarchy from CNN-based image classification refers to earlier layers learning more fundamental features like color gradients or basic shapes, and later layers building up on earlier layers. Oh, that's really helpful. So, okay, so it would be like kind of like if you're icing a cookie and you start with, you know, like the big frosting and then you flood it or whatever, and then on top of that you would put, you know, like the smile on the snowman or whatever you're doing. I don't know that cookie icing is a good metaphor that's accessible to everybody, but as you build up, you do finer and finer details. And what I'm getting from Sakar's comment is that the hierarchy of image features is sort of similar. You start with, you know, the broad strokes, and then you get finer and finer information as you go on. And correct me if that's wrong, but that's sort of what I'm synthesizing from that. We also show that BILM activations can be used to form phrase representations useful for syntactic tasks. Ooh. So it's sort of like those constituency things that I was talking about earlier, and some like words that go together in a sentence are like a chunk that you can do things with. So so like on the table, I put the pizza on the table, you could replace it with like there, I put the pizza there, and that whole chunk is sort of like replaceable in some way. I don't want to get too deep into the syntax, not least because I'm a wee bit rusty, and also because I would have to pick a framework, and I don't want to do that. Together, these results suggest that large-scale BILMs, independent of architecture, are learning much more about the structure of language than previously appreciated. Okay. I'm interested to learn more about this, especially because the last bidirectional language modeling paper we read, I was a little bit unimpressed with. I think it was an interesting engineering paper that was not particularly compelling to me. Roland Yu said, did you study linguistics in school or just something you've been interested in exploring? NLP? In a related topic, did you ever watch the movie Arrival? I did study linguistics, so I have, you know, the suite of degrees. I got my bachelor's, master's, and PhD in linguistics, and I haven't seen Arrival because I'm a very bad linguist, but I have read many articles written by linguists about arrival. And I know that people are fairly salty about the Sapir-Whorf hypothesis over-reliance in the movie. So there's lots of stuff out there if you're interested in that. All right, let's get into the math. A little sip of coffee. Contextual word representations from BLMs, bidirectional language models. To learn contextual word representations, we follow previous work by first training a BLM on a large text corpus, see section 2.1. Then the internal layer activations from the BLM are transferred to downstream tasks. Okay, so it seems fairly similar to the GPT-2 paper in that they train a language model and then they just, plug it into different tasks that they are interested in doing. All right, given bidirectional language models, section 2.1. Given a sequence of n tokens, T1 through Tn, a BLM contains a forward and backwards language model to jointly maximize the log likelihood of both directions. So for each token, k equals 1. Oh, k starting at 1. So you get the maximum log, so you get the log likelihood of tk given t1 through tk minus 1. So looking at everything in the sequence, every previous thing in the sequence, you get the probability of token k looking right and looking left, k plus 1 through n. Okay, so looking at everything before and everything after, you get the maximum, you pick the token that has the maximum log likelihood, where theta backwards and theta forwards are the parameters of the forward and backward language models, respectively. Okay. That makes sense to me. I hear a fan. One sec, I'm gonna go turn the fan off. I'll be right back. It was my heater, because it's a little bit cold here. We actually had hail last night. It was coming down, which I don't think I've seen in Seattle previously. So some sort of weather change over time, perhaps some sort of climate difference. I don't know. To compute the probability of the next token, state-of-the-art neural LMs first produce a context-insensitive token representation or word embedding. Is that a chi? I think that's a chi, k, with either an embedding lookup or, in our case, a character-aware encoder, see below. Context-insensitive token representation or word embedding. So this is just like your bog standard word embedding, glove, fast text, whatever you're using. Or maybe you have task-specific word embeddings. Then they compute slanty L layers of context-dependent representations. So vector HKI, forward-looking, where I is in the set of real numbers 1L, using a RNN, CNN, or feed-forward network, see section 3. Okay. Okay, L layers of context-dependent representations. Okay, so compute L layers of context-dependent representations using RNN, CNN, or feed-forward network. So each content-dependent representation is calculated using the language model above, a forward and backwards language model, And they do that for L number of layers. So if it's a 4-layer network, they would do it 4 times. K for the specific token. The top layer is used to predict the next token using a softmax layer. The backward language model operates in an analogous manner to the forward language model. Okay, so this is just the forward language model that we're talking about here. Finally, we can concatenate the forward and backward states to form L layers of context representations or context vectors at each token position. When training, we tie the weights of the word embedding layers and softmax in each direction, but maintain separate weights for the contextual layers. All right, let's go through that one more time. I understood some of those words. Okay, so we start with just our word embedding. So this is for a single token. We just start with our word embedding. And then we compute L layers of context-dependent representation, so looking forward, and then later doing the same thing backward using our network. And then the top layer is used to predict the next token using the softmax layer. So that's sort of the generative property. And then we do the same thing backwards. So instead of predicting the next token, we predict the previous token. And then we concatenate, so we're not adding them, we're sort of putting them together, the forward and backward states to form L layers of contextual representations. Okay, so we have one that's looking forward, one that's looking backward. We stick them together. Our sort of like vector embedding that we had is in the middle. And then we do that for each token position across each of the layers that we have. So this is pretty big, eventually. Leonardo says, like Elmo, I think. Yeah, that makes sense. We talked about Elmo in the BERT paper, which we read not last time, but the one before that. Esme says, does Resume Project, which is use scraped data, provide greater impression on interviews or project built with data provided online? That is out of scope for this particular stream, but if anyone has any ideas, feel free to jump in the chat and help me out. Okay. When training, we tie the weights of the word embedding layers and softmax in each direction, but maintain separate weights for the contextual layers. Tie the weights. The word embedding layers. Oh, okay, I see. Okay, just like Leonardo said, it's just like Elmo. So the embeddings, we've got like one layer everybody uses, and then we do forward facing, backward facing, and then we do softmax together again. So it's that sort of like that we looked at in the BERT paper. Okay, I think I'm picking up what they're putting down now. 2.2, character-based language models. Fully character-aware models, Kim et al. 2015, are considerably more parameter efficient than word-based models, but more computationally expensive than word embedding-based models when training. So in English, we have, 26-ish characters. We have many more than that words. So if you're, doing one-hot encoding, it's much easier to do with characters than it is with words, just because there are many words and you're going to end up with a super big sparse matrix. But it takes a lot more time to do operations on characters than it does on words if you're looking at a text of the same length, because most words are more than one character. Sort of what they're getting there. Flo says, with these bidirectional LSTMs, do they share a carry track, or are there new carry tracks moving forward and backward? What I'm getting is that there are, within the model, there's a forward-looking model that has like a shared first and last layer, and then there's a backwards looking model that has a shared first and last layer. I think there's a good picture of this in the BERT paper. if I remember. And that's my understanding from this paper. And if anyone else is more clear on it, please feel free to jump in. So it's sort of the representation that I'm understanding that they're using looks like this, if that answers your question. So we have the forward facing, the backward facing, and then everyone's using the same embeddings, input embeddings, and the same softmax layer, so you get one word output at each time point. Oops. Oh no, I made it big. Okay. Hopefully that's better. During inference, these differences can be largely eliminated by pre-computing embeddings for a large vocabulary and only falling back to full character-based methods for rare words. So if you've ever worked with something and you end up getting a lot of tokens that are UNK or unknown because they're out of vocabulary, like if you did watch any of the making text sound old-timey videos, our output was a lot of like unk, unk, unk. So one method of getting around this is to use word-based models where you have prior training information for the words, and then when you don't, you switch to character-based models, which are more expensive but more flexible. Overall, for a large English language news benchmark, character-aware models have slightly better perplexities than word-based ones, although the differences tend to be small. So for perplexity, you want it to be low, and it's sort of how... I guess you can think of it as like, how surprised are you to see this word? And the less surprised you are, the more you're expecting it, the better your grasp of the way the language works, kind of. I always get perplexity and entropy backwards, but I'm pretty sure that's the direction they go in. Okay. Similar to Kim et al. 2015, Leonardo says, Leonardo's answering It's Me's question, so thank you. Overall, blah, blah, blah. Similar to Kim, our character-to-word encoder is a 5-layer submodule that first embeds single characters with an embedding layer, then passes them through 248-character n-gram CNN filters with max pooling, 2 highway layers, Srivastava et al. 2015, and a linear projection down to the model dimensions. 5-layer submodule first embeds single characters within an embedding layer, and then looks at 248 character n-gram, so sort of like a sliding window of 248 characters at a time, and then puts that into a convolutional neural network with max pooling, 2 highway layers, don't know what that is, and a linear projection down to the model dimension. So you start with something pretty big, and then you want to, sort of like get it to the size that you want it to be. So, I mean, very common with convolutional neural networks. Also sort of similar to PCA in terms of dimension reduction. Principal components analysis, PCA. Ryan says, I would like to explain the model architecture, but I'm trapped by the 200-character limit. I think you have more than that in the comments if you'd like to leave a comment. Yeah, let's find out about highway layers. Because this is not something that I have heard about before. This is an extremely short Wikipedia article. In machine learning, a highway network is an approach to optimizing networks and increasing their depth. Highway networks use learned gating mechanism to regulate information flow, inspired by long short-term memory recurrent neural networks. The gating mechanisms allow neural networks to have paths for information to flow across different layers, information highways. Highway networks have been used as part of text sequencing labeling and speech recognition tasks. Okay, so it's a way to... I'm not... garbage day. I'm not entirely sure what information they mean here. But what I'm getting is that it is like gating in the gated convolutional neural networks that we talked about earlier, or the forget gates in long short-term memory. Ryan says, summary of highway network is adding additional connections to later layers in order to pass information deeper. Oh, so it sort of like goes around, it skips layers, yeah? That's what I'm getting from that. So that you'd have an edge, if you were looking at your graph, you'd have an edge, not like your fully connected thing, but you'd also have an edge going from, skipping layers in the intermediate so that you can have more connections between, Yeah. Ryan says, so you pass layers 1 output to layer 5. Okay, I get you. Cool. That seems interesting. And I guess it works good. Neural network architecture, 2019, excuse me. It seems interesting and I guess it works good. And Flow Adaptive says, sounds similar to a carry track, term from F. Cholet. Yes, also something I'm not familiar with, but the words seem similar. It also seems a little bit similar to the, in the Vaswani paper. But of course, this is across networks and not within the same network. The normalization layer where you sort of just like skip one subnetwork entirely before you go into the next network. Ryan says, hasn't worked in my experience, but the research says otherwise. It might be one of those things where you need like super specific like tuning to do it, and people are just like, oh, everyone knows you have to, lick your CNNs before you stick them in the actuator. Who doesn't know that? That's not a real thing. That's possible. Interesting. Okay. Gotcha. So the information that things are occurring next to each other and the position of them regarding each other. So the way that you're avoiding just saying like, this word is made up of some letters and it doesn't matter what order the letters are in, because that does matter quite a bit actually, as my teachers in 3rd grade were quick to tell me, is by using these sort of like sliding n-grams, and most words are more than 2048, are much fewer than 2048 characters. So it seems like you might even be getting a little bit of syntactic information in there, because you have sort of like a larger span that you're looking at. I'm gonna get this. Vamsikrishna. If I got that wrong, I apologize. That is 100% on me for being illiterate in that language. Highway networks similar to gated CNNs. I think Sorry, so if I'm remembering the thing that we looked at from the gates earlier, it is that part of the output is passed through a sigmoid feature and part of the output is passed around a sigmoid feature, and I'm getting that the highway networks are going around the rest of the layers of the network, but they'd still be passed out to the same output layer. Ryan says, my understanding of gated CNN is that it is just limiting the information going to the layer after. Highway network is allowing information to pass to other languages. Leonardo says, I thought 2048 is the size of the input sequence, and then N is the size of the tokens. Interesting. 5-layer submodule. So this is just in the, this is just the character to word encoder. So this is the first layer that I believe they're going to then split into the forward and the backward facing model, is what I'm getting with that. 2048 is the size of the input sentence. So usually with n-grams, you sort of slide over your text. So similar to like in a CNN, how you sort of like over the image that you're looking at. I mean, this is a CNN, so that's what they're doing. They're sort of like over the text. So you would be at the same time looking at different words, unless that's the maximum length. Hello, hello, Swaraj from Bangalore. Sorry, I'm not ignoring you. I'm just confusing myself. Yeah, but it does seem like a pretty long input sequence. Okay, so I'm getting that this is the input. Is there like a picture of your network architecture in here? Oh, I know I make fun of people for always putting pictures of their networks architectures in their slides, but I really would like a picture of the network architecture here. It would be helpful to me. And Wasim from India. Hello. All right. Deep contextual word representations. After pre-training on a large data set, the internal representations from the BILM can be transferred to a downstream model of interest as contextual word representations. So similar to the similar to the GPT-2 paper that we looked at, and also similar to BERT. It's sort of like it's almost like transfer learning. You've done some pre-training, and then you can add it to other tasks downstream. To effectively use all of the BILM layers, Peters et al., so this is the paper where they introduced the idea of contextual word and vectors, introduced Elmo word representations, whereby all layers, so it's exactly like the Elmo representation. Nope, it's in here somewhere. Show me the Elmo. Is it not in here? Oh, that's right. It was in the BERT paper. Nope. The PDF. So it's exactly like, here we go. It's exactly like Elmo. That's exactly the one that they're doing, because that's them and it's the work that they did. And I just made that connection. So noted. Introduced Elmo word representations, whereby all layers are combined with a weighted average pooling operation, Elmo. That sure are some Greek letters. None of these things are defined. Okay, well, we're just gonna say weighted average pooling, and if you want to learn more, go check out the Elmo paper. The parameters are optimized as part of the task model so that it may preferentially mix different types of contextual information represented in different layers of the BILM. The parameters S, oh, I see. So this is parameters. I have no idea what H is. L is probably layers. This, is that a lowercase lambda? I don't know what that is. That's a letter. Vamsik Krishna says, could you please give us a surface level understanding of Elmo? I can't, I'm sorry. I think the best surface level understanding is sort of this, which is the architecture that we talked about previously, where you're training two layers, two models, one facing forward, one facing backwards, both LSTMs with the same word embeddings as input, and then to get to this last layer, I think this is the Elmo step. This is the average weighted pooling representation. Weighted average pooling operation. Leonardo says H is the context-dependent representation. Okay, so S are the parameters. H is the context representation. J is the given word, I'm guessing. Because we're summing over. Oh no, so J must be the task. Okay, so J is the parameter, K is the token, L is the layers, and this guy, I don't know what this character is. Help me, Google. I can't even copy it? Can I not copy it? Oh, sorry, I made it big. I cannot copy it. No. Go back to being a good size. Do I want to exit? I don't want to exit. Gamma, Du Young and Panagoides say, it looks like a Greek gamma. Okay, and then J is the layer. Okay, so the parameters for the layer, the contextual representations for the layer, and I still think K is the token. We're doing gamma to it. And then we're summing over all... Wait, so if J is the layer, what's L? Because previously they combined... Oh, so L must be the number of layers. So it's the number of times you're doing it. J is each layer. Okay. I don't know what the gamma is doing. Leonardo says K is the token. Okay. That makes sense. Even though they have... Yeah. Okay, so previously they've used K to refer to the kth token. Yeah, I don't... Gamma sum. That must be the weighted. Sum of independent gamma distributions. Independent gamma gamma distribution. Gamma random variables. Approximation of the distribution. Oh, this is Greek to me. Flo says, from Zhang 2016, highway connections are an extension of deep LSTMs, providing direct connections that enable unimpeded information flow across different layers. Okay. Oh, and Josh also says gamma. They never mentioned gamma before, as far as I can tell. Yeah, I don't see it. I'm sure they mentioned it in the other paper. I'm guessing that it is the gamma that makes it a weighted average. And that gamma is a term that they learn, specify. I do not know. The parameters S are optimized as part of the task model, so S is learned, so that it may preferentially mix different types of contextual information represented in different layers of BiLM. In section 4, we evaluate the relative effectiveness of Elmo representations from 3 different BiLM architectures versus pre-trained word vectors in 4 different state-of-the-art models. Michael says S sub j corresponds to the weights, I suppose? Yeah, it would have to be because those are learned. Or at least optimized. This is the part of mathy papers I don't like, where they're like, no, here's some things we've never defined. Just figure it out. Just you figure it out. It'll be fine. Okay. So far, talking about the way that they're training their word representations, their contextual word representations, which is the whole point of the paper, is that this is a thing and this is how they do it. So they have sort of this bidirectional Elmo, they have this bidirectional language model, which looks like this, as discussed in the BERT paper. And then they, as the input to that, instead of linear production down to the model dimensions during inference, difference in pre-computing. Character to word encoder. So this must be the input embedding. Or are they doing, so they mentioned this thing where you only use word embeddings when you have words, and when something's out of vocabulary, then you turn to the character-based embedding. And I'm getting that they're doing this overall. So there must be like, and here's the thing that sometimes people do, but we're always using the character-based language models. We're using the character-word encoding, and then that encoding is the input to the bidirectional language model. And then after we're done with the bidirectional language model, we collapse them. We sort of pool them using Elmo, which is the weighted average pooling operation here. So what I'm getting is that here as the input we have our character word models, and then at this stage after it's done, we apply the Elmo weighted pooling, and then what we get out is sort of like a little portable language model we can use in different places. Leonardo says, I think gamma has to be the weighted average operation because they sum the representation for each layer, so you have to divide to get the average part. Sum the token representations from each layer. Yeah. Oh, okay, that makes sense. So it's not just the weight, but it's also the thing that is causing it to be average and not just the sum of everything. That makes sense. Okay, so I think I more or less, I pick it up, what they're putting down in terms of model architecture. And I think I'm going to start wrapping it up there because it is about 10 for me. And next time we will turn to, so the different ways that they, okay. Because I was like, okay, but here I'm thinking that this is an LSTM. So what they're saying is that you could have anything in here. It doesn't have to be an LSTM. It could be a CNN. It could be a fully attentive network. It could be whatever you like, as long as you have one facing backwards, one facing forwards. And then they are gonna talk about each of those models. I don't know how this is gonna work with transformers or CNNs, to be honest, because those face both directions at once. So sort of like look at everything at the same time. But we'll get to that when we get to that. Michael says, each mathematical definition has to be defined properly. Yeah, and the thing is, I mean, a lot of things are just sort of like convention, and if you've been working in the field, you're just sort of like, oh, yeah, of course, that makes sense. Why would gamma be anything other than, the weighted average? But if you're relatively new to the field or you're sort of coming into a new subfield and you haven't learned those conventions, then it's super opaque, which is one of the reasons that I sometimes find it easier to understand architectures from the code than I do from the math, because there's a lot of sort of like undefined, I don't know what that symbol means, and my Greek alphabet is awful, and I don't necessarily always know how to look up the symbols, so that's also a struggle. My friend who has a math master's gets a lot of like me texting him being like, what does the squiggly R mean? How can I find that out? So, yeah, okay, so when we come in on next Wednesday, we're going to talk about architectures for deep BLMs. Actually, let me check really quick. I'm going to be traveling like a lot coming up, so I'm going to try to always have it on Wednesday, but it may or may not be at the same time. Yeah, it might be a little bit more in the afternoon. I'll let you know. I'll tweet about it, and I will. I'll try and make the event on YouTube the day before, so you can see the countdown to what time it's gonna be. And I will let you guys know. But definitely, we'll be back next Wednesday at some time during the day on Wednesday, and I'll let you know as soon as I do. And we will talk about the different architectures that they're using and comparing to each other, which I'm excited about. I think this is an interesting paper. I think that they're making some pretty strong claims vis-a-vis the information that is encoded in each layer of the networks that they're training. So I'm excited to see some very robust evidence of these claims, and hopefully we will see that next week or the week after. And Mom says, next paper on dialogue, act tagging, and DAMSL. Yeah, if you've got a paper you'd like to request, feel free. So far, I have pretty much only read papers that people have requested, except for the GPT-2 paper, because I was just really curious about that one. Thanks so much for joining me today, guys. I will be live coding on Friday. I'm not 100% sure what I'm going to be doing yet. I've been thinking about doing something that's a little bit more introductory on machine learning and Arc, just because I have a lot of requests for it, and also I'm doing it anyway for something else, so I might as well reuse the content. But yeah, I'll tweet about it, and you'll see the title of the event when I make it. So thanks for joining. I hope you guys have a great day or great evening, depending on what time zone it is for you. And I will see you on Friday or next Wednesday. Bye.